All right, in chapter 12, section 4, we're going to look at the cross product. So this is another operation involving vectors. And the first problem is just going to be a fill-in-the-blank style problem. It says, show that the cross product looks like an X, so dot product looks like a dot, cross product looks like a cross, or an X, or a multiplication sign. And it says, okay, the vector V is V1, V2, V3, so just generic letters with subscripts to represent numbers. So the way you do the cross product is, if you're doing the first component, you cross through the first lines, and then you do what's called a determinant, a 2x2 determinant of what's left. So what's left is V2, V3, V2, and V3. Now generically, any determinant, let's say I have A, B, C, D, is equal to A times D minus B times C. So the way most people remember it is you multiply this diagonal and then you subtract going this diagonal. So that's called a determinant. Okay, so if we apply that same approach here, the determinant would be V2 times V3 minus V3 times V2. So let's write that. That would equal V2 times V3 minus V3 times V2. And they've done half of it for us, so they did this part, V2 times V3 minus, I guess I can type here. Okay, so I typed in there V2, V3. So I did swap these only because multiplication order does not matter, and they're going to want these to look the same, so you just take these two and swap them, and that's fine. So V2, V3. And you can see that those are the exact same thing, so they're going to subtract to be 0. Okay, then they get the second set of numbers by crossing off the second column. So they look at this and say, cross off the second column, and what you're left with out of that one is the I column and the K column, and that's V1, V1, and that's V3, V3, and the determinant of that would be equal to V1 times V3 minus V3 times V1. And they've written that right there. Okay, then the third one is going to be, we cross off the third column, and the determinant that's left is the I column and the J column, and that's V1, V2, V1, V2. And that's going to equal V1 times V2 minus V2 times V1. So it's going to be V1 times V2 minus V2 times V1. So we just have to type, let's see, they've given us the second one with the minus sign. We just have to type this one in right here. Okay, so if we look, we've typed in our two boxes, and then you can see that in each of these bubbles, you have the exact same terms, just their order's reversed, but that shouldn't matter. And so you're going to subtract the same things from each other, so you get 0, 0, and 0, 3 zeros, and in vector form, that's 0 in the I, 0 in the J, 0 in the K. So that would prove that a vector cross product with itself is equal to 0. And we'll explain more why that is as we go through this section, and I tell you more about what the cross product represents. Okay, for problem 2, it's mostly fill in the blank. So they give you vector A, vector B, vector C, and they want you to take A dotted with B cross C. So B cross C is going to be vector B, 3 minus 1, 3. So it's 3 minus 1, 3. That's vector B. Cross with C, which is 0 minus 5, 18. So it's 0 minus 5 from right here. and 18 and 18. So that's B cross C, that's this part. If I want to dot A with it, I can actually put it as its own row above these other rows. So this top row is just 4, 2, minus 8, 4, 2, minus 8. Okay, so that's how you do the first part. Just fill in the numbers in the right positions. Okay, now this creates the determinant of a 3 by 3. So the determinant of a 3 by 3 works like this. You take the first number and you write it out here, and then you take a determinant of the first column crossed off and the first row crossed off. So what's left is minus 1, minus 5, 3, and 18. And this is going to be 4 times minus 1 times 18 minus 3 times negative 5. So that's, again, that's that determinant, the 2 by 2. So you take minus 1 times 18, that's right here. Then you do minus, which is this way, so that's this minus sign here, 3 times 5. So this minus sign came from the order of the determinant, and then this 3 came from this 3, and this minus 5 came from that minus 5. Okay, so let's see. So they kind of lead you through that too. So they say, okay, if I pull the 4 out, what's the 2 by 2 determinant? It's minus 1, 3. So you have to type that 3 in there. And then they give you the minus 5 and the 18 right there. Okay. Then the order, or I should say the next thing you do is you grab the middle top number. So you kind of work this strategically left to right. You grab the middle top number, but you make it you flip the sign. So if it's 2, it becomes minus 2. And then you do the determinant of cross off that column and the top row. What numbers are left? 3, 0. This minus 5 should have been over here with this lined up. They didn't line them up great. And then 3 and 18 over here are left over. That's going to be minus 2 times the determinant of 3 times 18 minus, because that's the form of the determinant, minus, go this way now, the other diagonal. 3 times 0. And let's see here. So they've got the minus sign. Let's cover what they've got covered. They've already got the minus sign right there. Then you have to I had to type in the 2, and then they have this box here, 33018, 33018. So they've got it typed out. Okay. Then the last step in the 3 by 3 determinant is taking the top right number and pulling that outside. So you say, okay, now we're going to grab this number, minus 8, and then we're going to cross off the top row and the third column. What's left? 3, 0, minus 1, and minus 5. And let's see. So they've got the minus 8 right there. And then they've got the 3, 0. I had to type in the minus 1 and the minus 5. Okay, but let's look at what that determinant would be. It would be 3 times minus 5 minus this direction. So it's going to equal minus 8 times 3 times minus 5 minus minus 1 times 0. And so that's going to be minus 8 times minus 15 with minus 0, so it goes away. Okay, so I actually kind of erased it because we already looked at it. If we did the determinant of this one, it would be minus 18 plus 15, because the double negative, and you get minus 3 here. So this minus 3 came from actually doing this determinant, minus 18 plus 15, going this way. Then they have the minus 2 right here, And then this 54 came from 3 times 18 minus 3 times 0, which is 0. So that's where that 54 came from. This minus 8 came from right there. And then this minus 15 came from 3 times minus 5, and then minus 1 times 0. So 3 times minus 5 shows up right there. And then to finally do this, you're going to get negative 12 for this bubble, minus 108 from this bubble, plus 120 from this one, and it just so happens that this is minus 120 plus 120, and all that work for 0. Won't always happen that way, but the numbers they picked here just happen to work out to be 0. That's problem 2. Okay, here's a full-up cross product problem, so let's try it start to finish. We have two vectors, 9, 0, minus 3, and 0, 9, 0. So here's how you do it. You write I, J, K on top. Then you write the first vector next, so it would be 9, 0, minus 3. Then you write the second vector on the bottom, 0, 9, 0. This is going to equal, we're going to cover up let me write this 3 times so I can do this in one motion. Okay, so in the first one we cover up the first column and the first row, right here, sorry, and we're left with this determinant. So we have 0, minus 3, 9, and 0, and that's going to equal 0 times 0 minus, the other way, minus 3 times 9, which is going to be 0 plus 27. In the second one, we're going to cover up the second column and the second column and the first row. So you're always covering up the first row, but you're just going to move first column, second column, third column. In fact, let me do that. So the third one, cover up the third column and the first row, and we can write our determinants. Now, like the previous problem, there's a minus sign that crops into this. So there's going to be a minus out front of here, and then we get 9, minus 3, 0, and 0. Well, this is going to equal minus from out here, 9 times 0, minus 3 times 0. And that's just going to be 0 minus 0, so it's 0. Okay, and now this is the ith direction. This is the j direction. And then the last one is going to be 9, 0, 0, 9. And we're going to get 9 times 9 minus 0 times 0, which is 81, and that's in the k direction. So let's type that in vector form. Actually, let me write it first. In vector form, that would be 27, 0, 81. Okay, now in the second part, they want us to calculate the dot product of this vector, this cross product, with the original two vectors. So let's look at that. So we would take 27, 0, 81, dotted with the first one they want us to do is A, 9, 0, negative 3, and recall dot product takes the first with the first, the second with the second, and the third with the third. So it's going to be 27 times 29 or times 9 plus 0 times 0 plus negative 3 times 81. And this is going to equal 243 minus 243, which is 0. So we can say that the cross product dotted with one of its constituent vectors is 0. I'll explain more why that is in a little bit. Let's try the second one. This says take A cross B, which is 27, 0, 81, dot that with the B vector, which was 0, 9, and 0. So once again, dot product matches the first two numbers, the second two numbers, and the third set of numbers, and you multiply them. So we're going to get 27 times 0 plus 0 times 9 plus 81 times 0. And this one's even easier. I've got a 0 multiplied into each term, so the whole thing is just going to equal 0. The reason for that is the uniqueness of the cross product. The cross product, when you calculate it, it finds a vector that is orthogonal or perpendicular to the two vectors. So, and we learned in the previous section that if you have vectors that are orthogonal or 90 degrees apart, their dot product is always 0. So this has to be true always. So as long as we got our cross product right, if we dot product that with either of the vectors that made the cross product, we should always get 0. Okay, and 4 is going to prove that again, so let's take a look at that. It's very similar. We have the cross product between A, which is, notice there's no I component, so there's 0 here. 1j, so 1, and then 9 in front of k, so 9. The second vector is 3i minus j, so minus 1 plus 2k, so it looks like that. Now I'm not going to show you all those three, I'm going to just kind of do this. If you imagine covering up the first column, the four numbers left are 1, 9, minus 1, and 2. Then the order is always plus, minus, and plus. So that's another way to remember it. The order on the cross product is plus, minus, plus. Now imagine covering up the second column. You would be left with the 0, the 9, the 3, and the 2. Now imagine covering up the third column. You'd be left with the 0, the 1, the 3, and the minus 1. So this is going to equal 2 plus 9, and that's in front of the I component, minus 0 times 2, which is 0, minus 9 times 3, which is 27, that's in front of the j, plus 0 times minus 1 is 0, minus 1 times 3, which is minus 3 in the k direction. So we're going to get 11i plus double negative 27j minus 3k. And we'll write that as 11, 27 minus 3. And in this one, I'm not even going to show it. If I dot that result with the vectors that I started with, I should get 0. So I just type zeros in there, not even going to double check it, and I get it right because I know that the dot product of a cross product and one of its constituent vectors will provide zeros. Okay, let's take a look at 5. 5 is actually, oh, okay, they do want a cross product. So this should not be that bad. We do I, we do j, we do k, and then a is 1 in the I. There's no j written, so 0, minus 6 in the k. The b vector, there is no I, so 0. The j component is 1, the k component is 1. And that's going to give us plus a determinant, minus a determinant, plus a determinant. And these numbers that go in these boxes cover up these different columns. So imagine covering up the first column completely. The four numbers left are 0, minus 6, 1, and 1. Imagine covering up the second column, the j column. The four numbers left are 1, minus 6, 0, bottom left, and 1, bottom right. Imagine covering up the third column, the k column. The four numbers are 1, 0, 0, 1. Now you do the determinants, so it's 0 times 1, 0, minus minus 6 times 1, so it becomes plus. 6 times 1 is 6. That's in front of I. Minus 1 times 1, minus 6 times 0, minus 0 in the J. Plus 1 times 1 is 1, minus 0 times 0 is 0 in the K. So we should get the vector 6, comma, minus 1, comma 1. Okay, and we got that one correct as well. Okay, so let's look at problem 6. It says find the vector not with determinants but by using properties of cross products. So it turns out that if you do if you write ijk like this, the cross product of I times j equals k. Let's actually show all these. So I cross j will give you k. If you do j cross k, you will get I. And then the last one you can do is if you do I, j, k, and you put the cross product here, it's actually going to be k cross with I, and that will give you j. So these, if you write it in alphabetical order, I, j, k, and then you do, if you move the cross product from left to right, you get the other letters. So I cross j is k, j cross k is I, and k cross I is j. So if we have I cross j, this is going to be a k. And then we proved k cross k, any vector cross with itself is just 0. And it's vector 0, so it's going to be actually 0, comma 0, comma 0. So that would be the result there. And notice you do want to write 000 in a vector form because, like a dot product gives you a scalar, a cross product does give you a vector back out. So you have to write it as a vector. If you write 0 by itself, that's a scalar. It's a different magnitude. It's a different dimension than a vector. Okay, let's see if we can go through problem 7. It says state whether each expression is meaningful or not. So we had seen this in the previous section. So B cross C, that's going to be a vector. So this is going to give us a vector out. And then we're dotting a vector with a vector. Well, that's going to equal a scalar. But it does have meaning. So we're going to say the expression is meaningful. It is a scalar. Okay, how about this one? We're given a vector and we're crossing it with B dot C is going to give you a scalar. Well, with the cross product, you have to use the cross product with two vectors and you get a vector out. So this one will not have meaning because you can't cross a vector and a scalar. So let's see, is meaningless. The cross product is defined only for two vectors. Okay, how about this one? A cross B cross C, this looks good. This is going to be a vector, B cross C is going to be a vector, and then you're crossing it, so you're going to get a vector out. So this is, the parentheses gives you a vector, and then you crossed out with a vector. Bunch of vectors here. This is meaningful. It is a vector. This one, when you dot B and C, you get a scalar, and you have a vector A dotted with a scalar. That is not going to have meaning because the dot product has to take two vectors and it gives you a scalar out. So this one is meaningless. The dot product is defined only for two vectors. Here you're going to get a scalar out and then you're trying to cross it with a scalar. Well, the cross product is only defined for vectors. So this one is meaningless because the cross product is only defined for two vectors. Last one, A cross B will give you a vector. You're dotting it with C cross D, which is going to give you a vector. That has meaning. It will provide a scalar. So this will have meaning, and the answer is a scalar. Okay, so again, We've seen these types of problems in the past 2 sections now, understanding this idea of dot products, cross products, scalars, vectors, and how they mix and match. Okay, let's try 8. Shouldn't be too bad either. More practice with cross products. So it wants us to do A cross B. A is 2 minus 1, 6, and B is 7, 2, 1. This is going to be plus, minus, plus. The numbers, cover up column I, you would have minus 1, 6, 2, 1. Cover up column J, 2, 6, 7, 1. Cover up column K, you would have 2 minus 1, 7, 2. And then these determinants become minus 1 minus 12, I, minus 2 minus 42, J, plus 4 minus minus, so it's plus 7K. So we get minus 13 comma, this is going to be minus 40, but double negative, so it's plus 40, and then 7 plus 4 is 11. Actually, I'll type that in a second. Okay, so let's do the other one. The other one they want us to do is IJK, reverse the order of these vectors. B cross A. Now, order does matter in vectors, and we'll see this in a second. So it's 7, 2, 1. B goes first now. Then A, 2 minus 1, 6. This will equal plus determinant, minus determinant, plus determinant. Cover up I. You should have 2, 1, minus 1, 6. Cover up J, 7, 1, 2, 6. Cover up K, 7, 2, 2 minus 1. This will equal 2 times 6, 12, minus minus 1, so plus 1 in the I, minus 7 times 6 is 42, minus 2 times 1, which is 2 in the J, plus 7 times minus 1 is minus 7. Minus 2 times 2 is minus 4 in the K. And we get 13, comma, minus 40, comma, minus 11. And what we should notice is that these two vectors are exactly negatives of each other. So minus 13, 13, positive 40, minus 40, 11, minus 11. So reversing the order of a cross product flips the sign on the result. And we can see we have that one correct as well. So to save time, you could just do one of these and then flip everything for the answer on the second one. Okay, problem 9, we've got find 2 unit vectors orthogonal to both. So 2 unit vectors orthogonal to both. That just says take a cross product. So I just have to take a cross product. The answer will be orthogonal to the other 2 vectors between 4, 2, 1 and minus 1, 1, 0. So this is going to equal plus determinant minus determinant plus determinant. Cover up I, 2, 1, 1, 0. Cover up J, 4, 1, minus 1, 0. Cover up K, 4, 2, minus 1, 1. And this is going to equal 2 times 0, which is 0, minus 1 times 1, which is 1 in the I, minus 4 times 0 is 0, minus 1, so plus 1 in the J, plus 4 times 1 is 4, minus 2, so plus 2 in the K. This vector is minus 1, comma, minus 1, comma, 6. Now they want us to make this a unit vector. So we would take that vector and divide by its magnitude, which is the square root of minus 1 squared plus minus 1 squared plus 6 squared. And that's going to be equal to minus 1, 6 divided by the square root of 36 plus 1 plus 1, the square root of 38, and I'll have to see if that simplifies. It does not, so this is just going to equal minus 1 over root 38 minus 1 over root 38 and 6 over root 38. Okay, now there's a second vector in here as well, and that would be if I reversed the order and made these negatives. So there's another vector here. It'd be positive 1, minus 6. And it's going to have the exact same magnitude because the numbers didn't change, other than minus signs, but those go away when I square them. So it's the exact same. In fact, let me just show you the unit vector then. So this unit vector would be 1 over root 38, positive 1 over root 38, and minus 6 over root 38. So those are the two unit vectors, and I want you to take the smaller I value first. So the I values are the first numbers, the smaller one will be the negative one. So this first vector will go in the first box, and this second vector will go in the second box. Let me type it in. And we type those in. It's a little tricky. You've got to have these square roots in the bottom and these minus signs right, but you can see they're pretty much exactly the same numbers except for they're swapped the minus signs, and we have problem 9 correct. Okay, for problem 10, they give us 3 points and they want us to find an orthogonal vector to the plane for which those points lie on. So first we just have to find 2 vectors that connect these points. So let's do PQ, which would be minus 2 from Q minus the x component of P. So basically you just subtract these 2 points, and then you subtract these 2, and then you subtract these 2, and we'll get a vector. So it's minus 2, 1 minus 0, and 3 minus 2. So the PQ vector is minus 4, 1, 1. Then we find the PR vector, which will be now between P and R. So we will look at the first 2 components of P and R, the second 2 components of P and R, and the third components of P and R. So it's going to be, starting with R, 6 minus 2 from P, comma, 2 from R minus 0 from P, comma, 4 from R minus 2 from P. And the PR vector is 4, 2, 2. And now we just have to take the cross product of PQ and PR. And that's going to equal PQ was minus 4, 1, 1. PR was 4, 2, 2. So this is going to equal plus determinant minus determinant plus determinant. Cover up the I column, you would have 1, 1, 2, 2. Cover up the J column, you would have minus 4, 1, 4, 2. Cover up the K column, you would have minus 4, 1, 4, 2. Interesting that those are the exact same determinant. Let me make sure I didn't make a mistake. Yep, they look good. Okay, so this is going to equal 2 minus 2 in the I minus 8 minus 4 in the J plus minus 8 minus 1 times 4 is 4 in the K. And that is going to equal 0I minus 12 of the minus, so plus 12J, and then minus 12 in the K. So we're going to have, oh, I guess I started to write that in vector form. Let me write it as 0, 12, minus 12. So that is going to be the non-zero vector that's orthogonal to these 3 points. Okay, in the second part of this, it wants us to find the area of the triangle created by those 3 points PQR. Well, it turns out that the area, let's see if I have room for this, is equal to 1/2 the absolute value or the magnitude of the vector created by the cross product. So it's 1/2 the magnitude of PQ cross PR. But we just found PQ times PR, so cross PR. So the area is 1/2 the magnitude of 0, 12 minus 12, which is 1/2 times the square root of 0 squared plus 12 squared plus minus 12 squared. And this is going to give us 1/2 of the square root of it basically gives us double 12 squared, 2 times 12 squared. Well, 12 squared can come out of this as 12. I wish I had more room here. So we're going to get the area is 1/2 times 12 times the square root of 2. The area should be 6 square root 2. Okay. And it got a little messy in there, but hopefully you can follow with the different colors. We got them both right. So you're given 3 points. Find the vectors between combinations of 2 of those, 2 out of 3 of the points. Do a cross product of those resulting vectors. That gives you the first answer. Find the magnitude of that resulting vector by squaring each component and taking a square root, and then just take half of it, and you'll have the area. Okay, in problem 11, they give us 4 points, P, Q, R, and S, and they say find the volume of the parallelepiped with adjacent edges PQ, PR, and PS. So we have to find PQ, PR, and PS. And we just do this by subtracting point Q from P, point R from P, and point S from P. I'm going to jump to that. I'm not going to show you that because we've done it many times by this point. Okay, so we would get those 3 vectors. Now the area of the parallelepiped is called the vector triple product, and it looks like this. It's the magnitude of A cross B dotted with C. So for our values, it's going to be PQ cross PR dotted with PS, and then take an absolute value. So let's look at PQ cross PR. So PQ cross PR would equal I, J, K. PQ is 6, 2, 4. PR is 3, 3 minus 1, which is going to give us cover up I, you get 2, 4, 3 minus 1. Minus sign from the order, plus, minus, plus. Cover up the J column, 6, 4, 3 minus 1. Cover up the K column, 6, 2, 3, 3. This is going to equal minus 2 minus 12 in the I, minus 6 minus 12 in the J, plus 18 minus 6 in the K. This is going to equal, in vector form, negative 14, comma, minus 18, but it's negative again, so positive 18, comma, 18 minus 6 is 12. Now, that is, let me use color to help us here, that is this. Then they want us to dot that with PS. So dot PS, which is 5, 5, 2, and we're going to match the first 2, the second 2, and the third 2, and we're going to get this dot product will be minus 14 times 5 plus 18 times 5 plus 12 times 2. And if you do that, you're going to get 44. Now, there is an absolute value around this, which just means it's an area you can't have a negative number. So if this turns out to be negative, well, negative areas don't make sense, so you're just going to report the positive value. Mine was positive, so it didn't matter. 44 in my case. And that's the area of a parallelepiped. Parallelepiped, I've heard it said different ways. Okay, problem 12. Use the scalar triple product, so that's what we just talked about. So the scalar triple product is the absolute value of A cross B dotted with C. And these are all vectors. Okay, so they want us to use U, let's see here, U, V, and W. So let's use their letters, U, V, and W. Okay, so U cross V would equal I, J, K. I'm only going to show a few more of these, and then I'm going to kind of jump to what the product would be. Let's do a few more for practice. 1I, 4J, minus 2K for U. V is 2I minus 1J and no K value, so 0. So this is plus, minus, plus. Cover up the I column, 4 minus 2 minus 1, 0. Cover up the J column, 1 minus 2, 2, 0. Cover up the K column, 1, 4, 2 minus 1. And I guess it's been a little while, so let me show it again. You do this multiplication and then subtract the other way. You do this multiplication and then subtract going the other way. You do this multiplication and then subtract going the other way. So to do this, you get 4 times 0, which is 0, minus, okay, you got triple negative here. Minus 2 times minus 1, which is positive 2, but there's a minus inherent in this backwards multiplication, so you get minus 2 out of that. In the I direction, minus 1 times 0 is 0, minus minus 2 times 2, so plus 4 in the J, and then plus minus 1 minus 8 in the K. So we get negative 2 comma 4, oops, minus 4 from that minus 9 in the K. And we just did this. Now we have to dot that with W. So dot that with, the W vector is 6, 11, negative 6. And we'll match up first 2 numbers, second 2 numbers, third 2 numbers, and we're going to get minus 2 times 6 plus minus 4 times 11 plus minus 9 times minus 6. And if you do all that out, you will get, for my numbers, I get negative 2. So are they coplanar? So if they were coplanar, that would have to equal 0. So are they coplanar? The vector triple product should equal 0. They are not coplanar if it doesn't equal 0. So our number was not 0, so we'd say no, they are not coplanar. Coplanar means they're on the same plane. So if I were to plot those 3 dots, I would get, they would all lie on the same plane, which these do not, because the scalar triple product was not 0. Okay, for 13, there's a hard way to do it and there's an easy way to do it, and I'm going to show you the easy way. So it says, a bicycle pedal is pushed by a foot with a 60 Newton force as shown. The shaft of the pedal is 12 centimeters long. Find the magnitude of the torque about P. So magnitude of the torque about P. Round your answer to one decimal place. So it turns out in physics, torque, which is a vector, is equal to the, let me write this a little differently. It is equal to the radius vector cross product with the force. So you could, in this case, the radius vector would be from this point to P, so it would look like this. And the force vector is right here. So based on those two things, you could create a three-dimensional vector called force, or in 2 dimensions, I guess in this case, a 2-dimensional vector called force and a 2-dimensional vector called R, cross them, and then take the magnitude, and you would get the answer. There is an easier way, and that says this: the magnitude of the torque is just equal to the magnitude of the radius vector times the magnitude of the force vector times the sine of the angle theta between them. So the only tricky part to this question is you have to realize that theta is this angle, which includes the 70 and the 10. And they gave us the magnitudes. So they said it's a 60 Newton force. That is the magnitude of R, not R, F. That is the magnitude of the force. And it told us that the radius vector is 12 centimeters long. So that is the magnitude of R. Okay, so all we have to do is take the magnitude of R. Now be careful, they want the units in meters, so you have to convert 12 centimeters to meters by dividing by 100. There's 100 centimeters per meter. Times the magnitude of force, now that's in newtons, which we want, so times 60 times the sine of the angle between them, which is 80 degrees. So make sure your calculator's in degrees, make sure you divide 12 by 100, and you should get 7.0906 Newton meters, and rounded to one decimal place, we'll call it 7.1 Newton times meters. Okay, so I did try this problem both ways, creating a vector R and a vector F, not impossible, but quite time consuming, and this is a much faster way, so there you go. Okay, hopefully these next ones are a little faster, and we don't have to do a lot of arithmetic here. These are true-false questions. So it says determine whether the statement is true or false. For any vectors u and v in V3, that's supposed to be an R, it just means that it's three-dimensional vector. U cross v equals v cross u. We already saw this. When you swap the order of the cross product, they differ by a minus sign. So they are not equal. Okay, for any vectors u and v, the absolute value of u cross v equals the absolute value of v cross u. Now this one is correct, because when you take an absolute value, the minus sign goes away. Those would be accurate. You'll get the same overall number. Now, when you take a magnitude like that, it's actually a, you do get, it's called the norm, and you get a number. That's where you take the square root of the component squared. But again, any minuses will go away in that calculation, so you get the same value. Okay, for any vectors with a scalar k, u cross v equals ku cross v. Let's actually try this one because we saw how it worked with dot product, but we haven't seen how it works with cross product. So I believe the way I did this is I just made a u and a v vector, so let's try it. Let's just assume u is equal to, I did 1, 2, 3. And then I said, let's just make up a v, doesn't really matter. Well, it matters a little bit. You don't want to make these like the same numbers or opposite by a minus sign. You want them to be different enough. So I think I made v 4, 5, 6. So notice the numbers are different between the two vectors, and you can't multiply u by any common number to get v, so they're different enough. Now if you do this, u cross v, and I'm not going to show it because I think I've shown you plenty of these by now, turns out to be -3, 6, -3. Okay, now and then I said, okay, let's come up with a k. So let's say k is equal to, what did I pick here? I'm not seeing it. I think I picked k was 2. So now it says take k times this. So k times u cross v, just double those numbers, -6, 12, -6. Okay, now we're going to, in this side it says first take k times u. So k times u, just double the original numbers, 2, 4, and 6. Then take that, cross it with v. And if you do this, you will get, okay, and if you do this one, you will get the exact same result out. So we can take some scalar k and multiply it by the resultant cross product, or we can take that k and multiply it by one of the two vectors first and then take the cross product. So notice the difference in order here. Cross product first, then the k first, then the cross product, and we will get the exact same answer. So that one's true. Okay, for 17, we have u plus v cross w, and then u cross w plus v cross w. So if you do this one, so notice they're messing with the order here. They're saying first add these two vectors, then cross product, or cross product these two separate vectors and then add. And I'm just going to kind of jump to the chase here for this one. If you do this, you will get the same result. So this one's true. Okay, for any vectors u, v, and w in 3 dimensions, first cross two vectors and then dot them with u, or first cross the other two vectors, then dot them with w. Again, if you work this out, you should get the same answer. So this is scalar triple product, and well, not quite scalar triple product because we didn't take an absolute value. And in here it shows that order doesn't matter. So cross product the first two vectors, dot it with the third, or cross product the second two vectors and dot it with the first, you'll get the same answer. And again, I proved all these just by picking random vectors u, v, and w and trying these, but I'm going to save you some time just by telling you what the result is. You can practice this yourself and prove this would be good exercise in cross products and dot products if you're so inclined. Okay, now 19. Notice the difference here. Dot product, cross product. So if you do cross product now and you mess with the order, it will not work. And that's because we saw how when you take cross products of swapping orders, you'll be off by a minus sign. So this one's not going to work. Okay, determine whether the following statement is true. If you cross u and v and dot it with u, that equals 0. So u cross v will be a vector that is orthogonal to both u and v. And when you dot product that with u, let me actually try to draw this. It's not easy, but let me try to draw this. If you have vectors u and v, the cross product produces a vector that is orthogonal to both. Orthogonal means that it is a 90-degree angle to both vectors. So it's a 90-degree angle with u, and it's a 90-degree angle with v. You can kind of see that in 3 dimensions. So then if I go and dot product that with u or v, so now I take u cross v, and I dot that with u, Or if I take u cross v, we saw this earlier, but it helps to see the picture. Well, the dot product between any vectors that are 90 degrees apart is always 0. So this one is true. Okay, let's look at the next three. 21. U plus v cross v equals u cross v. So if I add u and v together, all that did was stretch. That creates a vector that is just a stretched version of the original u vector. Then I cross it with the same vector v. Well, the vector that's orthogonal to those two will be the same as if I just crossed u and v by themselves. Sounds true. For 22, it says if the cross product is 0, then either u is 0 or v is 0. This is just like we saw last time. Just because you get 0 out does not mean that your vectors are zeros, because you could get these vectors that the numbers line up in such a way that you get some negative, some positive. They could all cancel each other out, and you could get zeros out. So this one's false. 23, if the dot product is 0 and the cross product is 0, then u is 0 or v is 0. So this one actually is true. So the cross product being identically 0 vector, that could happen where the vectors are non-zero. But also their dot product being 0, now that's getting a little fishy. We would have to say, okay, if their dot product's also 0, then we must have one of them to be 0. Okay, last two. The dot product between two vectors, absolute valued, has to be less than the magnitudes of either vector multiplied. This one should be. Okay, this one is true because if you recall what the dot product is, the dot product is equal to the absolute value of the magnitude of u and v times cosine theta. Well, notice that these two parts are exactly the same. And cosine theta will always be bound between -1 and 1. So the biggest this can ever be is when cosine is 1 and you get uv equals uv. That's this equal sign right here. But typically cosine is going to be smaller than 1. So half, third, something like that. So this is always going to be actually smaller than this side. So this one's true. Okay, for the last problem, it says the cross product of two unit vectors is a unit vector. So we showed that that was true for I, J, and K. But you could have a unit vector that is not just I or J or K. You could have some combination of numbers that their magnitude is 1. But that does not guarantee that when you cross those two vectors that you get a unit vector out. So that one is false. And that will complete section 12.4.